So this particular video goes over the method of substitution as a means to find antiderivatives. So recall the fundamental theorem of calculus. If a function is integrable on a closed interval, we almost always just use continuity, and f is any antiderivative of the function on that interval, then you can find the value of the definite integral by evaluating the antiderivative at the bounds and then just subtracting. This, of course, requires us to find an antiderivative, and we now need more techniques to do so. Use substitution is a method based on the chain rule. It's just in reverse. It's a means to integrate a product where one of the factors is a composition. Assume that capital F is an antiderivative for lowercase f. That means if you want to find the derivative of capital F with a function g using the chain rule, you would then take the derivative of the outside function, getting, in this case, lowercase f. You would not change what the function was applied to, but then you would multiply the result by the derivative of that inside. Now, in our case, though, you can write that exact same thing in terms of a integration. Notice it's the integration of a product where one of the factors is a composition. The result is to take the antiderivative of the outside function, the function being applied to something else, and then don't change what it's applied to. So it's still a composition in the end. And then the derivative of g would be reabsorbed back in when you undo that chain rule. Now, use substitution is a way of doing that same thing, but symbolically. So here's the same integration. Let's just say that u is g of x. Then we know from differentials that du is g prime of x dx. You could then replace those things in the integrand, converting the old integral into a new one. Notice that the two integrals, one's entirely in x, one's entirely in u. You should never write down an integral that has x's and u's at the same time, even briefly. But then we know the antiderivative of little f. It's capital F, and we just don't change the inside. It's u. That's the answer. I mean, that's the answer in terms of u. We wanted the answer in terms of x. So we'll just put the u back with what it's equal to. So we get the answer, capital F of g of x plus c. The same answer we had before. So this is the u substitution or composition type pattern. You're looking for a composition of some kind, a function of something. The integrand, ignoring that composition, should equal the derivative of the inside of the composition, multiply the dx. You identify whatever the inside is and call it u, compute the differential, and you just replace all expressions in x with expressions in u. Notice the integral in the beginning is all in terms of x, and the new integral is in terms of u. So u substitution just converts it to a new integral. It doesn't actually finish the problem. I'll do a couple. If you look at this particular integration, I see a product, and there certainly is a composition as x squared plus 3. I'm taking the fourth root of it. So I'll make u be the inside of that parentheses, and du then be 2x dx. By just reordering it to make it look more obvious, putting the 2x right next to the dx as it's multiplication anyway, I'll put a little box around the x squared plus 3 to the fourth power, and put a circle around the 2x dx. That way I've identified the substitutions. And outside these circles and boxes, there shouldn't be any x's. That way I now know that I can do a clean substitution. So I know what the x squared plus 3 is, it's u. I know the 2x dx is just du, and that is my new integral. So then I can do that integral and get that this is equal to 1/5 u to the 5th plus c, and then I can replace the u. After all, that's the answer in terms of u. I want the answer in terms of x. So I'll replace the u with what it's equivalent to, giving me, in the end, the correct antiderivative. Doing that again, if you look at this in particular integration, there certainly is a product. Then the composition is the square root of 4x plus 1. So I'll let u be 4x plus 1. So du would then be 4 dx. I don't have a 4 times dx, though. Well, that's okay. The constant 4 doesn't really affect much. I'll just divide the 4 on both sides. Then, by just rearranging terms, if necessary, I put circles and boxes around the x's for my substitutions. My 4x plus 1, I'll put a box, that's just u. Everything else has to have a circle around it if it has an x. I know what dx is, it's just 1/4 du. That gives me that new integral. I'll then just go and clean it up to write it as the antiderivative of 1/4. I'll write the square root of u as u to the 1/2 du. We can then take the u, increase the power by 1, And then we'll multiply by the reciprocal of that power, giving us 1/6 plus c. That's the answer. That's the answer in terms of u, at least. We wanted the answer in terms of x. So I'll replace the u with what it's equivalent to get 1/6 4x plus 1 to the 3/2 power plus c. That's the antiderivative of the original function. So I went and showed you earlier on in the course the method SAPDO, which is S-A-P add do. Each one stands for a certain step you do for integration. I show this to my students just because it seems like it's a way for them to remember the results. It is not the only way to do it. There's many ways to learn how to do integration. This is just what I do. So the S in this method stands for think simple. Can you simplify the integrand? If you can, do so. When you write things in a standard way, you have a better chance of recognizing the problem and then proceeding from there using your experience. The next step there would then be, do you recognize the integrand as a standard one that you've memorized or have done previously? If so, use those techniques. If not, then if it's a sum or difference, you might want to consider breaking this one integral into multiple ones, hopefully each one simpler. It means consider it, doesn't mean do it. The A in SAPDO stands for algebra. Here your goal is can you convert the integrand to become a sum or difference of constant multiples of functions you know how to integrate, because then we can use previous steps to integrate it. So if you see a multiplication, try distributing. That will then turn into a sum. If you see a fraction, try separating it. Turns it into a sum. If you see a rational function, try long division. That turns it into a sum. If you see monomials where you could write them using rational powers, try it. You might recognize it as part of a sum or something else. Now in the method, the SAP add do method, the P stands for patterns. There's just general patterns that when you see them in an integrand, you use a certain technique. So if you have, for example, a function raised to a power, you're making u be the function being raised to a power, and you're hoping to get this kind of integral. On the other hand, if you see fraction, you might want to try u being the denominator or a factor of that denominator, because you might get lucky and get this kind of integral. If instead the denominator has a sum or difference of squares, you want to make u be the function that's squared as that part of that sum, because you might convert the integral into one of these three. If you see a exponent that's a function, then you might want to try u as that exponent, because you might get this integral. Let's try a few of them. So in this particular integral, I notice there is a composition right here, the secant of 4x. So I'll try u equals 4x. That means then du would equal 4 dx, so that dx would equal 1/4 du. I see this is part of my substitution, that is part of my substitution, and this dx already has something for it. So this becomes the integration of the secant of u, the tangent of u, and remember it's all multiplied together, so let's multiply what dx is. Dx is 1/4 du. So I'll just skip a step and put the 1/4 right in front and put the du here and back. Now I can see that as 1/4, and we know the antiderivative of the secant of u times tangent of u. It's just the secant of u plus c. That's the answer. Well, I mean, that's the answer in terms of u. We wanted the answer in terms of x. So I'll replace the u with what it's equivalent to as a function of x, and that gives me the answer. I'll do it again. And the next integral, notice there's a proc, and there certainly is a composition. Right here, there's a function being taken to the 4th power, so it's the 4th power of something. So I'll let u be that inside that composition and just hope it works. Then du will then equal to the cosine of x dx. That means that the inside is the sine of x, and the cosine of x is being multiplied to this dx, so that's also taken care of. This integral then becomes the u, the 4th power, and the cosine of x times dx is just du. So that antiderivative is 1/5 u to the 5th plus c. Or it's 1/5, the u is the sine 5th power of x plus c. And that is the antiderivative. Now this particular method can be kind of sneaky because you have to pick the right substitution. Notice these two integrals look very similar to each other, but they'll have very different substitutions. And the first one, I would say u should then be 16 minus 9x squared, because then du will then equal negative 18x dx, and I'll solve what I need for. See the x dx, that's what I need right here. The 2 I don't worry about. So that's a negative 18 du is equal to x dx. So the expression inside the root, that's the u, because it was the square root of something. And the x dx, that product, also has something for it. So everything has an x inside everything that has an x is inside either a circle or a box. This then becomes the integral. Everything else remains. So I still have a 2 in the numerator. I still have a square root, but now it's applied to the square root of u, and the x dx becomes a negative 1/18 times du. I'll just clean that integral up to get a negative 1/9 square roots of u du. Now that integral is pretty easy to do because I can rewrite this square root as u to the 1/2 and bring it up into the numerator, changing the power from positive to negative to get u to the negative 1/2 du. And then we take the u, we increase the power, we'll multiply by the reciprocal of that power to get, this is the answer. Well, this is the answer in terms of u. I wanted the answer in terms of x. So I'll replace the u with what it's equivalent to as a function of x. And since I have a half, I'll write it as a square root. That would then be 16 minus 9x squared, and then finally plus c outside the square root. That's the answer. Doing it again, this time though, notice the derivative of the inside of the square root has an x, and there's no x there. That's how I know not to make u be 16 minus 9x squared, because its derivative would be off by more than just a constant. So I'll try this time, let u equal to 3x, then du will equal 3dx, and I'll get 1/3 du is equal to dx. That means that this part right here is actually u squared, and that is 1/3 du. So I get the new integral of 2 over a square root of a 16 minus u squared, and dx is 1/3 du. So that's the same as the integral of, now think of it as 2/3, the antiderivative of the square root of 16 minus u squared du. And we know how to integrate that. Take the 2/3 out. You have 1 over the square root of 16 minus u squared du. And we recognize that as one of the arc function rules, so it's the arc sine. So that is 2/3 the inverse sine of u over 4 plus c. That's the answer. I mean, that's the answer in terms of u. I wanted the answer in terms of x, so I will replace the u with what it's equivalent to. So that would be a 3x over 4 plus c. That's the antiderivative for that one. Last two examples. If I wanted to find this particular antiderivative, I notice there is a composition. I see a e to the x squared, so it's e of x squared. So I'll make u be the exponent, x squared. Then du will equal to 2x dx. That means 1/2 du will equal to x dx. Notice that I have something for the x squared, and the x and the dx are multiplied together, so I can replace them. This becomes the integral. The 4 stays behind, the e to the u stays behind, and the x dx becomes 1/2 du. Just clean that up, you get 2 times e to the u du, and that is clearly then just 2 times e to the u plus c. And we know what u is. I'll just put it back. So you have 2 times e to the x squared plus c. That's the antiderivative. Doing it again. Now the u substitution can really be used in almost many cases. So here, it's kind of sneaky to see though. What I would try here is see the natural log. I hate this guy. We're going to get rid of him for sure. Because finding antiderivatives that have natural logs in them is challenging. So if I make u be it, maybe I'll get lucky and it'll go away. But there's no cost at all to put the 4 with it. No cost at all. So I'll do that. That would then mean then du would equal to just 1 over x dx. You can see why I didn't care if the 4 was put in or not, because this derivative just vanishes. This then becomes the antiderivative of, well, this is my substitution. The x divided into the dx is right here. So I have a u over a 5 and a du. That's my new integral. Just making it look nice, that's 1/5 u du. And we know that would then be equal to, you take the u, we increase the power, and then we multiply by the reciprocal of that power. That would then be 1/10 plus c. Just replacing u, you get 1/10, 4 plus the natural log of x squared plus c. And that's the antiderivative for that problem. You probably have noticed that many of our antiderivatives so far have been, I pick a u, I then compute du, I then divide by a constant, get a constant times du is some substitution, and then that constant actually persists all the way through the integration. There's a good reason for that. If you look at a technique called correction by constants, you can basically do these integrations a lot faster in very specific cases. It's better though to learn the overall technique because u substitution is extremely useful beyond just this. So for example, if I wanted to find this particular antiderivative, I'd let u be k times g, then the derivative of u, or the differential in u, would be k times the derivative of g times dx. You then move the constant to the other side, you get 1 over k du is the derivative of g in terms of x times dx. Just by replacing things, I then get this new integral. Assuming we know that antiderivative is capital F, let's say, you would then get 1 over k, capital F of u, plus c. I could then go and replace u for what I know it equals, which is k g of x. That gives me an answer, 1 over k times the antiderivative of the outside. We don't change the inside, and we drop the derivative of g and get c. So look at the beginning, look at the end. Notice that you take the antiderivative of the outside operation, you do not change the inside, and you just drop the derivative. And since the derivative of the inside, I was missing the constant, I divide by the kissing that. And since the inside of that composition was k times g of x, that derivative was k times g prime of x, I was missing the constant. In the end, I wound up dividing by the constant that was missing. So, this particular technique is not something I really want you to do in Calc 1. I'm showing it to you so you can do these integrals a little bit faster once you get beyond Calc 1. You're okay to use it later on after this course, as long as you never get it wrong. Just want to show you the technique a few times. So I suppose I want to know this integral. I look at it and see the inside is 3x squared. That derivative is 6x. I don't have a 6x. I have a 2x. I'll put the 2 on the outside, and now I notice that I'm missing the constant of 6. So ignore the x and look only at the operation being applied to 3x squared. The antiderivative of secant squared is tangent. So it's the tangent of the inside, and I divide by the constant that was missing. And the 2 was still there. That's the antiderivative. That's doing u substitution, but now in your head. Doing it again. Let's say I want to find this antiderivative. I notice I have a composition. The inside is 3x plus 5. The outside is squaring. The constant 4, don't worry about it, we'll just put it out front. The derivative of the inside is just 3, but I'm missing a 3. So I will go and take the antiderivative of the outside by increasing the power and multiplying by reciprocal. I'll keep the inside, 3x plus 5. The 4 as a multiplication will still be there. And I divide by the constant that was missing. I divide by 3. That's the answer. All you have to do is simplify it. And of course you add your c. Let's use the same technique, but this time with a definite integral. Remember, when we are finding a definite integral, we have to find an antiderivative first. And we treat the definite integral like it's an antiderivative symbol for as long as possible. So we'll use u equals x plus 1. Then du will be dx. So the question would then be is that would this definite integral be the same as that one? When you do this, it's hard to understand maybe, but you're actually going from one system, an xy plane, to a new system, a uy plane. When you look at those two different regions over the different axes, notice that the regions are clearly not the same size. In fact, the areas are clearly not the same. But the mistake is that I didn't actually change over all the x values into u values. See, the integration from 0 to 1, those are values on the x-axis, so they're x values. I must convert them also. So to do that, here's our integral, and if x is 1, u is x plus 1, so u is 2. If x is 0, u is x plus 1, so u is 1. So the new integral should be from 1 to 2 u squared du. And in fact, if you look at those regions, you get the exact same region. So of course they're the same area. This is called changing the bounds. Whenever you go and use the u substitution with a definite integral, you must, when you change the variable, you change the bounds. If you don't, notice that you probably don't get the same answer. And these are numbers. The numbers, they must be equal to each other or it doesn't make sense. So let's do that again. I'd like to know the value of this definite integral. So noticing there's a composition and it's a definite integral, I'm going to use that when I change the variables, I will change the bounds, as you can see right here. To do so, we'll make u be the inside of the square root like always, du then be 1/2 dx, so dx will then be 2 times du. But then also, since I have bounds for x, I'll make a chart. I'll keep all the u's on one side, all the x's on the other, same as I have the equations above. And I'll make sure the order of the x values are the same as what you see in the integrand. So when x is 2, by our substitution, u has got to be 2. When x is 0, u has to be 1. So this definite integral has to equal that one. Now I just proceed. So to find this definite integral by the fundamental theorem of calculus, I can evaluate that by finding an antiderivative. I'll rewrite the integrand so that I use a rational exponent. I'll add 1 to the exponent, multiply by the reciprocal of that particular power to get the antiderivative 4/3 u to the 3/2. I'll then evaluate that at 1 and 2 and subtract. When you do so, you get that number. Notice by changing the bounds, I never did the step of going back to x. That's why when I do antiderivatives, I always keep saying to you, that's the answer in terms of u. I want the answer in terms of x, because here I don't want the answer in terms of x. I want a number. So you never have to go back to x. You just do it with the new bounds. It's the same as doing it without. Now another thing is though, if you look at the two integrand, the square root of x plus 2 over 2 from 0 to 2, and 2 times the square root of u from 1 to 2, and you plot them on their separate x, y, and u, y axes, you get those pictures and they're not the same. They don't have to be the same. The only thing I'm guaranteeing is that the areas are the same. The regions don't have to be. So remember, after the substitution, the region, the interval, the graph, they can all be the same. But the definite integrals will be equal as long as when you change the variables, you change the bounds. Now in the technique I give you, SAP, add, U, the S stands for simplify, A stands for algebra, P stands for particular patterns, in this case it's the composition pattern, U substitution. The add stands for advanced manipulation techniques. It's things where you shouldn't try this stuff until you try everything else. So using trig identities, trying completing the square, multiplying and dividing by the exact same expression. These are all things you try after you try everything else. And then if it's really, really bad, you get to the very last step, which is U for uh-oh, something really is bad. You have to try something. The only thing you can try at this point is U substitution. Try U as something. So I wanted to show you some of these more difficult integrands just so that you have experience with it and you might be able to recognize it on your own. Here, if I went through all the process, all the different steps, eventually I would come to, let's try u equals x minus 3. That means my du would then equal to dx. I'd have a box around my x minus 3 and I have something for dx, and sadly that x is still outside. That means that the substitution won't work. Well, it won't work as far as you're used to. After all, we have a relationship between u and x. Just solve for x. You get x equals u plus 3. Now we have something for the x also. So this becomes the integration of u plus 3 times u squared du. At this point, now I'll just distribute the product to get the antiderivative of u cubed plus 3u squared du. That would then be 1/4 u to the 4th plus u cubed plus c, and that's the answer in terms of u. I wanted the answer in terms of x, so I'll just replace the u with the expression that's equivalent to get 1/4 x minus 3 to the 4th plus x minus 3 to the 3rd plus c, and that's the antiderivative. Here's another one. Notice in the denominator it is not a sum or difference of squares because that 6x messes up things. No substitution as of right now, the way it looks, will be something we could convert this into an integral that we could then recognize. But I noticed though that the denominator, by completing the square, can be written this way by rewriting the 25 as 9 plus 16. That then is the same as x plus 3 squared plus 16. So if you rewrite the integral as 4 over x plus 3 squared plus 16, now if we make u equal to x plus 3, so du will just be our dx, the integration now becomes 4 over u squared plus 16 du. And we recognize that as the inverse tangent rule. So the answer is 4. The antiderivative of 1 over u squared plus 16 du, that is 4. You have the inverse tangent of u over 4 plus c, and there's a 1/4 because of this 4. This then is the inverse tangent of u over 4 plus c, and that's the answer in terms of u. I want in terms of x, so I'll replace the u with what it's equivalent to, which here is x plus 3. And that's the antiderivative. As one last example, let's find this antiderivative. Now our normal techniques of making u be the inside of the square root will not lead us anywhere, because if I make u be that particular quotient, the derivative of that quotient would be another quotient, and there isn't another quotient outside the square root. Instead, I'll use some sneaky little algebra manipulations. Rewrite this as the square root of 1 over x to the 4th times x minus 1 over x dx. That then equals the integration of, you get the square root of 1 over x to the 4th and the square root of x minus 1 all over x dx. But that's the same as writing the antiderivative of 1 over x squared, square root, and then separate the fraction. You get 1 minus 1 over x dx. The reason I did that is, if you make this now be u, its derivative is 1 over x squared. So if u equals 1 minus 1 over x, then du will be 1 over x squared dx. The integral now becomes the antiderivative of the square root of u du. And we know how to integrate that. Just take the u and write it to the 1/2 power instead. Then increase the power by 1 and multiply by the reciprocal of the power and add c. Then we know what u is, so I'll replace it with what it's equivalent to, 1 minus 1 over x, and that's to the 3/2 power plus c. And that's the antiderivative for that problem. That gives you a basic introduction on the method of substitution, both for antiderivatives and also for evaluating definite integrals once you change the bounds.